Good day students, I am Dr. Smita Sharma and today we'll talk about practical op-amps. So in the previous lecture that we had taken up, we had discussed about virtual ground. What do you mean by virtual ground and why it is used, and how can we calculate voltage gain using voltage gain of inverting and non-inverting amplifier using virtual ground. This we have all discussed. Now up till now we have discussed operational amplifier for an ideal case. Now we'll consider practical op-amp. So when we take a practical op-amp, what additional things are introduced in the operational amplifier basic circuit? So while considering practical op-amp, we say that it has some DC output voltage called output offset voltage, even though both inverting and non-inverting input terminals are ground. So if we ground both the inverting and non-inverting terminal, what will happen? There will be no input signal, but in spite of no input signal, there is some output voltage or output is still present for a practical op-amp. Such an output voltage is an error voltage because we are not giving any input signal, but output is there and it is undesirable. So here in this lecture we'll discuss what are the properties that cause this voltage to develop and how can we minimize these effects. We will also see that it is necessary to incorporate additional circuitry to increase the effectiveness of the op-amp, especially if it is used as a DC amplifier. So here we'll be taking up operational amplifier again, but we'll discuss how can we reduce this output offset voltage. We have already discussed output offset voltage, and we have also discussed some other properties of the operational amplifier due to which this output offset voltage arises. In this lecture we will see the techniques how can we reduce or eliminate this error voltage. So first of all we'll take up the input offset voltage and output offset voltage. Now first of all we'll define input offset voltage. It is the differential input voltage that exists between two input terminals of an op-amp without any external inputs applied. So what is we are not applying any input, but still there is some input. There is some differential input between inverting and non-inverting terminals. That is input offset voltage. In other words, it is the amount of input voltage that should be applied between the two input terminals in order to force the output voltage to 0. So you can always say that how is that possible that we are not applying any external input but still there is input differential input between the two terminals? No, this doesn't exist, but we are not giving any input, still there is some output. So in order to reduce that output to 0, we have to apply some input signal in order to reduce that output voltage to 0. This additional applied input signal that makes output 0 is the input offset voltage. We denote output offset voltage by VOO and input offset voltage by VIO. The output offset voltage is caused by mismatching between the two input terminals. So basically output offset voltage is due to mismatching between the two terminals that are present in the input. Now why this mismatching occurs? Because even though all the circuit is designed on a single chip, but still two transistors that are designed on the same chip are not completely identical. There is some mismatching, and due to this the differential amplifier stage is not completely identical. This means that the collector current in these two transistors are not equal, which causes a differential output voltage from the first stage. So if there is mismatching, then differential output voltage will appear in the first stage only, and that this differential output voltage keeps on amplifying in further stages. The output of the first stage is amplified by the following stages and possibly increased due to mismatching in them. Thus, the output voltage caused by mismatching between two input terminals is the output offset voltage. This now we can completely understand it. The output offset voltage is a DC voltage. So it can either be positive in polarity or negative in polarity, depending on whether which terminal is is greater. If the positive terminal is greater, then we will have positive polarity, and if negative terminal, that is inverting terminal, is greater, then we will have negative polarity. It is impossible to predict the polarity of input offset voltage since it is dependent on mismatching between the two input terminals. So we cannot predict input offset voltage, what type it will be, because we don't know the mismatching, what category of mismatching or what type of mismatching occurs between the two transistors of the two stages. So we can only say that it is either positive or it is either negative. Now this we have discussed input offset voltage and output offset voltage. Now we will see how can we reduce it. What are the measures that we can take in order to eliminate it so that it does not affect our actual results. Generally, input offset voltage in the data sheet provided by the manufacturer, it is only its value is given, maximum value is given. It is not written positive or negative because we cannot predict it. So to reduce output offset voltage, we need to have a circuit at the input terminal of the operational amplifier that gives us the flexibility of obtaining input offset voltage of proper amplitude and polarity, and such a circuit is called an input offset voltage compensating network. So what is necessary? We want to reduce the output offset voltage. For that we need an additional circuit that is to be connected in the input terminal, and circuit should work in such a way that the input offset voltage that we obtain to reduce the output offset voltage to 0 should be of proper amplitude and polarity, so that it helps us in reducing the output offset voltage to 0. In other words, or simpler words, we can say that the external circuitry that we apply in the input terminal should be flexible or adjustable, so that we can change it according to our needs. It should not be fixed. Before we apply external input to the operational amplifier with the help of offset voltage compensating network, we reduce the output offset voltage to 0. The open is then set the op amp is then said to be nulled or balanced. So what do we do? First of all, we apply this circuit. This circuit is connected before using the operational amplifier, and first of all what we do, with the help of that external circuit, we reduce the output offset voltage to 0, and then we start doing the application for what that operational amplifier is made. At this position, when no external inputs are applied, and with the help of input circuitry we have nulled the output offset voltage, or output offset voltage is 0, then we say that operational amplifier is in nulled position or balanced position. Now here it is worth noting that compensating network is not needed for those operational amplifier that have offset null pins. So here you should remember that for every IC op amp it is not necessary we have an external compensating network. If in a IC there are offset pins, null pins available, then we use offset null pins to nullify the effect of output offset voltage. For example, in 741 we do not need an external circuitry. Null pins are available, and by applying a suitable potentiometer we can easily nullify this effect. So here in figure 741 is being shown with you can see here between 1 pin and 5 pin a potentiometer of 10 kilo ohms is applied, and its wiper is connected to the 4 pin, number 4 pin. For 741 type op amp, the manufacturer recommends that a 10 kilo ohms potentiometer should be placed across offset null pins 1 and 5, and wiper be connected. Wiper, what do you mean by wiper? That movable pin. Wiper be connected to the negative supply pin as shown in the figure. Adjustment of this pot. So this is potentiometer, and if by suitable adjustment of this pot we can nullify the output. So for 0 input we can get a 0 output by the help of simple potentiometer. By varying the position of the wiper on the 10 kilo ohm potentiometer, we are trying to remove the mismatch between inverting and non-inverting input terminals of the operational amplifier. So for such operational amplifier having null pins, we can simply apply a potentiometer between the null pins, and the wiper that is movable pin should be connected to the negative supply pin. That will serve the purpose. So what is first case of reducing output offset voltage? Simply apply a potentiometer between pin 1 and 5. Now we'll discuss input bias current. Its definition we have already studied, but we'll discuss once more. The input bias is defined as the average of the two input bias current IB1 and IB2 as shown in figure. So basically input bias current is IB1 plus IB2 upon 2. Here IB1 is the DC bias current flowing into non-inverting input, and IB2 is the DC bias current flowing into the inverting input. Now as you can see in the figure, both the terminals inverting, non-inverting and inverting both are grounded. But plus and minus supply are present to bias the op-amp properly. What does biasing means? Biasing means to apply power supply to the given instrument. So here we are supplying the two power supplies and reducing both the inputs to ground. Actually, the input bias current are the base bias current of the two transistor in the input differential amplifier stage of the op-amp. In order to see what does input bias current means, we go back, you can remember the differential amplifier circuit. We had two stages of common emitter amplifier stages that were connected together to form a differential amplifier, and input was given through base of both the transistor. So basically the input bias current is the difference between the two base bias currents. To base current, if both the base currents are different, then input bias current arises. And this, why does this will arise? This will again arise because two transistor, howsoever they are made, they are not completely identical. So internal imbalance between the two input arises this current. Even though very small input bias current can cause a significant output offset voltage in circuit. So although this input bias current is very small, but it generates a very high output offset voltage in the circuits. So it is necessary to eliminate it or reduce it. So what we can do, it is a simple method. We can reduce both, we can make both V1 and V2. What is V1 and V2? V1 and V2 are voltages at inverting and non-inverting inputs. We can make, if there is some reason, if there is some way to make both the two voltages equal, then we can reduce or eliminate the input bias current. So how can this be done? This can be done by using a proper value of resistor ROM connecting in the non-inverting terminal, which is parallel combination of resistors R1 and RF. So what we can do, as you can see from the second diagram, we can connect a resistor ROM, and ROM is equal to parallel combination of R1 and RF. We first calculate the parallel combination of R1 and RF, and then the value that comes out, that resistor is applied here at the non-inverting end. This helps us in reducing the effects due to input bias current. The use of this resistor minimizes the amount of output offset voltage. Therefore, resistor is referred to as offset minimizing resistor. So this ROM is what its name is. Its name is offset minimizing resistor. Now next is input offset current. Now we know input offset current, we have already studied its definition before. It is the algebraic difference between the two input bias current. That is I is simply IB1 minus IB2. So input offset current, for a given value of input offset current, the amount of output offset voltage depends on the value of feedback resistor. So again here also the output offset voltage that arises due to this current depends on the feedback resistor. Again, by using proper value of resistor, we can minimize the output offset voltage due to unequal input bias current. So because input bias current reduces the output offset voltage, the same resistor can be used to reduce the input offset current also. So total output offset voltage arises due to input offset current, input bias current, and input offset voltage. It is observed that output offset voltage would be either positive, negative with respect to ground. Also the use of resistor in non-inverting or inverting amplifier assures a reduction in the current generated output offset voltage. So there should be a resistor applied in non-inverting end and the inverting end that assures us that the current that is generated because of output offset voltage will be reduced to zero. So this should be taken up. So here what we have studied up till now, we have studied that two things you should do before using operational amplifier practically. First, null pins should be connected with the potentiometer and an additional resistor should be connected in the non-inverting end at least. So this is the minimum thing that should be additionally added along with your circuit. Suppose you are running some application of the operational amplifier, like we are using it as an adder circuit or integrator circuit. So we make the basic circuit, but we should always remember to add these two components also, potentiometer and this resistor, compensating resistor, in order to reduce the effect of output offset voltage. There are some more things that affect the efficiency of the operational amplifier, that is temperature, voltage fluctuation in the power supply fluctuation. These are also effect that drifts the that introduces the output offset voltage and makes operational amplifier less workable. So the input offset voltage and current tend to drift with change in temperature drift. So these two values change with the temperature. So because of this they introduce an undesirable error voltage that is not needed. This error voltage actually affects the accuracy of amplifier when it is used as a DC amplifier, and it also limits the amplitude of AC signal that can be amplified without distortion. So this error voltage should be reduced to minimum. The input offset voltage of the op-amp also changes with change in supply voltages. So the supply voltages should remain constant, because if input offset voltage changes, this will change output offset voltage, and again the operational amplifier will not function so well. To keep this to minimum, a regulated power supply should be used so that there are no fluctuation, or op-amps with relatively high supply voltage rejection ratio, CVRR. So high CVRR operational amplifier should be used. So this is all problems with the practical op-amp. So these two additional circuitry should be added in along with the circuit that is used to make operational amplifier to perform some mathematical operation or task. And it should always be remembered that ideal op-amp, there is difference between a practical op-amp and an ideal op-amp. Also here CMRR of the operational amplifier also becomes important parameter, because if CMRR is more, then operational amplifier can reduce the error voltage or the noise signal in a better way rather than an operational amplifier having less common CMRR. So these are the main basic properties that should be remembered. So now in next lecture we will discuss the frequency response of the operational amplifier. These after discussing with the frequency response of the operational amplifier, we will be able to use operational amplifier in our linear applications. So so in next lecture we'll discuss its frequency response. Thank you.